Hello everyone. In this video we're going to review some concepts involving measurement as well as the different types of units that we would see when we make measurements in a chemistry lab. So measurements and measurement calculations allow chemists to determine quantitative properties of a substance. Remember in the previous video we discussed that with qualities or qualitative properties or observations we're looking at kind of what it looks like, what it smells like, what it feels like, things like that, things that you can actually observe with, your vision and your senses and things like that. With quantitative properties, we're dealing with numbers. So often chemists have many unique tools that allow us to effectively measure the presence of some sort of property. So whether it be length or volume or mass or different things like that. So we use measurements for that. And as a result, we'll also use some calculations to convert between different measurements to allow for a convenient measurement. Measurements are recorded during an experiment, but calculations can be performed during or after an experiment. But usually, most chemists will wait until the experiment's done so they can focus on the actual lab work, and they'll do those calculations at the end or at the completion of the experiment. So we have measurements and we have calculations. We're going to do some work with some of that stuff in the next couple videos. So let's look at the base units of measurement. According to the SI, which stands for the System International or International. Okay. So this is a national, or not just national, international organization, because it's international. That basically for all science it's really helpful for us to have standard units to make measurements in, because if one country does all of its measurements in a particular unit and then another country does it in a particular unit, it's very tough to convert back and forth, and it needs to be standardized. So we use base units, part of the SI system, to do a lot of these. For length, the SI unit for length is the meter, and we use a lowercase m to abbreviate that. We discussed this in a previous video, but with mass, the kilogram is the official unit for mass. However, keep in mind this is for all science, so we like to use grams, which is just lowercase g. However, for many other sciences such as physics and things like that, kilograms is what the standard is there. Kilo is a prefix meaning 1,000, and that's going to basically represent 1,000 grams is a kilogram. Time, the standard unit for time is the second, which goes in S. Also, it just makes things a lot easier with seconds, because often if you think of chemical reactions, some of them take some time, maybe take minutes or hours depending, but most that you'll see in our class happen in seconds, or in many cases even shorter than 1 second. Temperature, we use the absolute scale known as Kelvin for temperature, that's a capital K. For electric current, we use the amp or the ampere, which is a capital A. And for the amount of substance that's present, we use the mole, which, look at this abbreviation, the unit is the mole, the symbol is MOL. These mean the same thing. The A is just a formality without any, it's just the abbreviation. Now, one thing to keep in mind is that as a chemist, you're going to be dealing with hexillions of atoms in just, a small quantity. So, for example, if I were to have 1 gram of hydrogen, an extremely small amount to us amount of hydrogen, that's 602 hexillion, that's, 21 zeros at the end of it, atoms of hydrogen to make up that, 1 gram of hydrogen. So, as I'm sure you know, we're working with very, very small things, so we're using a lot of submultiples. However, if we blow them up to amounts that we can actually handle with our hands, we're going to be dealing with very large values of really small things, right? So we have to make sure we're familiar with converting units, because it is so annoying to write all of these zeros out to discuss things, and it's really hard for scientists to interpret, right? So the base unit is what we saw on the last slide, but if we add prefixes to those base units, it makes it a lot easier for us. So for example, some of these prefixes are more appropriate to measure certain things. So if I were trying to look at, for example, the amount of bytes on a hard drive, it wouldn't make a lot of sense for me to say, all right, that'll be one with 12 zeros after it, bytes of memory. You know what I mean? Or, basically 1 billion. I'm sorry, 1 trillion here. This is a trillion, my bad. 1 trillion, bytes. That doesn't make a lot of sense, right? Especially if you have other numbers up in here, that makes it very difficult to do. So what we can do instead is saying 1 trillion bytes, I can say, well, I have 1 terabyte. Or instead of billion, I can say I have 1 gigabyte. So you'll commonly see things with like hard drives on your computers and stuff like that. If you think about measuring the length of your fingernail, you're not going to necessarily use meters to measure your fingernail because it would be a very small number of meters. It would be a decimal amount of meters. So instead, maybe you'll go ahead and use centimeters to measure the length of your fingernail, right? So we use prefixes to represent measurements in an easier way. You have to know by memory the prefixes, the symbols, and the value that connects those. So, for example, let me show you what I mean. Let's say I have 1 kilogram. How many grams is that? Well, kilo is 10 to the third power, so that's indicating to me that for every 1 kilogram, one big thing, I'm going to have 1,000 of the lesser thing make it up. So it's 1,000 grams. So whenever you write conversion factors with your prefixes, you're always going to put the number 1 next to that larger prefix or that larger unit. So let's do another example. Let's say I have 1 gram. How many nanograms is that? Well, if I have one big unit, 1 gram, how many smaller nanograms makes that up? I would say 1 times 10 to the 9th nanograms makes up 1 gram. It's a lot of small things in one bigger thing. So these conversion factors we'll get into in a future video, but they're very, very useful in converting units, especially when we use dimensional analysis, or what's also referred to as the factor label method to convert units. Now, the base units, there's the ones that we just discussed. However, scientists and chemists can do math with certain units to give us units that maybe are more useful. And these units are derived. They're derived units. They're derived because you have to do a mathematical combination or computation to arrive at whatever those units might be. So in chemistry, ones you'll see a lot of, volume, believe it or not, is a derived unit, and density is another derived unit. So for volume, I'm sure that if you were to find the volume of a cube, for example, perfect cube, all the sides are the same length, you would find that it's basically side cubed. It's basically your length times your width times your height. That gives you your volume. So if you think about it, I'm essentially taking a base unit of length. Remember, the base unit for length is meters. And if I cube it, now I have a derived unit. It takes meters times meters times meters. Now, this is commonly confused because if you take water, for example, and put it in a beaker, you're measuring volume. You're measuring it in milliliters, or you're measuring it in liters. However, there's a conversion we can use for this. For every 1 milliliter, that is equal to 1 cubic centimeter. And then you can do some math, and you can derive that 1 liter is equal to 1,000 cubic centimeters. Okay? We'll get into some math like that later with dimensional analysis, but these are good to know. Okay? These are good units to know here. Another common chemistry unit is density. Now, if you've taken a course previous with me, you can do D equals M over V, or density is equal to the mass divided by the volume, but I know a lot of you kind of liked the little pyramid here, where you do D, and you do M, and you do V. And we use this so we can solve for whatever unit. So let's say you're trying to solve for mass. What do I have to do? Take the density, multiply it by the volume. So it goes left to right, it's like you're multiplying. If I have, let's say, volume, or let's say, actually, I'm trying to solve for volume. I take mass and I divide it by density. That'll give me volume. So you can use this little triangle, the DMV triangle, to help you figure that stuff out quickly, or you can solve for a single variable like you would in math. So again, that's a ratio of mass over volume. Again, mass is a base unit. Kilograms is the base unit, but remember in chemistry we're going to use grams more often than not. And volume, I don't know why I put capital, oh, because it fills in the equation here, sorry. This should be M, not a G. Mass over volume. Again, we can rearrange to solve. You can use the triangle here, or you can solve for a single variable. What's important to keep in mind is that density allows us to save equipment and allows us to make simple calculations to solve for mass, as an example. So think of it this way. If I wanted to pour a liquid into a graduated cylinder, I can identify the volume very quickly. And then if I know the density of that liquid, and I know the volume of that liquid, I can figure out the mass of that liquid without ever putting it on a scale. Because if you think about it, trying to put liquids on a scale, what if it spills? It could short circuit your scale and you're out $1,000. So, or maybe a little bit less if it's a cheaper scale. So we want to make sure that, we can use derived units to solve for things that are actually doing a lot of work. Now, with every measurement that you take, whether it be measuring with a graduated cylinder or using a manual scale, a balance type thing, a triple balance, there's going to be some uncertainty. It's never going to be totally perfect. So in labs, chemists often take measurements by reading markings on an instrument like a graduated cylinder. In many cases, readings will not be perfectly on the center of a line. So it's not going to line up perfectly in the center. Since there's a slight amount of estimation, we refer to this as an uncertainty in measurement. The final digit in a measurement is always estimated, with the previous digits being certain. So let me show you what that means. Let's say I have an object here. And let's say I'm measuring it on a ruler. Okay, and I'll make some general markings here to kind of give you an idea. Let's say I have 1, I have 2, 3, 4, 5, as an example. Now I can tell, looking at this object here, this is the object I'm measuring, I can tell that this object is definitely past 3, and it's definitely not past 4. So I'm certain it's 3, right? But 3 what? Well, given this picture, it looks like it's around maybe 3.4. That 0.4 is a total estimate, right? I'm not certain if it's 0.4. I could say 3.5, and that measurement would be what's considered valid because I have the most amount of certainty plus an estimated digit. So whenever you take a measurement, you're always going to go as accurate as your markings allow you to identify, plus an extra digit that's an estimate. Oftentimes, you might see things like this. You might see like 3.4 plus or minus 1 or 0.1. So basically what that's saying is, well, I'm not so certain. It could be 3.4, but plus 0.1, it could be 3.5, or it could be 3.3, because 3.4 minus 0.1 would be 3.3. So we can use these as a way to properly measure objects and account for any uncertainty. So whenever you take a measurement, your final digit is always going to be an estimated digit.